We will now study a class of metric spaces that are the most important for the purposes of this course and in much of mathematics. These are the so-called normed vector spaces. A vector space in which you can measure the distance to the origin. So let me just state the definition right away. Definition: we will deal only with real vector spaces, but much of what I say can be easily extended to the case where the vector space is a complex vector space. Let V be a vector space over R. A norm on V is a function and motivated by our use of parallel lines to denote the absolute value in the real numbers, we will use these double parallel lines from V to R to denote the norm function, and this bold dot is just an indicator that that's where the variable goes. So we have this function norm from V to R such that first property, which is positivity, norm V is greater than or equal to 0 for all V in V, and norm V equal to 0 if and only if V is 0. This is somewhat intuitive. If you are measuring the distance to the origin, of course you are always going to get a positive quantity, and furthermore the only quantity which is 0 distance away from the origin is the origin itself. Second property is the fact that if V is in V and C is a scalar, then norm of CV is just mod C norm V. Okay, again a perfectly reasonable requirement. If you scale the vector by a C, constant C, then the length of the vector or the distance to the origin of the scaled vector will also get scaled, but not by C but by absolute value of C, because distance does not have a positive or a negative sign. 3 is the triangle inequality. Norm of V plus W is less than or equal to norm V plus norm W. This captures the intuitive fact that we have in the vector space R2 and the usual distance that you have in R2, that sum of the lengths of two sides of a triangle always exceeds the third side. Okay, a normed vector space is a vector space equipped with a norm. Let me just remark that many people call vector spaces linear spaces, and normed vector spaces will be called norm linear spaces. Usually abbreviations are used. NVS or NLS or some such variant is used for the sake of brevity. So because of the importance of this last property, let me just name that. So this last one is the triangle inequality, which we spoke about, and it's going to be the one that we are going to repeatedly use in the future. Okay, so let me just immediately give you a very easy exercise. If V is a normed vector space, then define, let's not say defining, define dxy by definition to be norm x minus y is a metric on V. Okay, so let me just even delete this word define. It plays no role in the definition. If V is a norm vector space, then dxy defined by norm x minus y is a metric. This means that all normed vector spaces are metric spaces in a natural way. So the idea behind choosing this as the definition of the metric is rather obvious. You know how to measure distance to the origin, therefore you know how to measure distance between two vectors. You just take the difference between the two vectors and measure the distance from the origin of that vector. Okay. Now, before giving examples, let me give a more refined notion of a normed vector space, which you are no doubt familiar with from linear algebra, called an inner product space. Now, the reason why I want to give this definition is because the most interesting vector space in this course is, of course, Rn, and that Rn, the underlying norm, comes from the inner product defined by the usual dot product or scalar product that you have studied in multivariable calculus. So this is the definition of an inner product space. Inner product space. Again, the setting is same. Let V be a vector space over R. An inner product is a function which has two slots. It eats up a vector cross a vector, that is a pair of vectors, and it outputs a real number for you, such that, of course, certain natural properties have to be satisfied. The first one is again non-negativity. If you take a vector and take its inner product with itself, you always get greater than or equal to 0 with equality if and only if V is 0. Let me just remark that this first property is often called positive semi-definiteness. Second is symmetry. VW is equal to WV. Needless to say, all these properties that I am writing down hold for any pair of vectors coming from this vector space. And the third property is just saying that if you leave the first slot empty and fix W in the second slot, so this will be a map from V to R for a fixed W. This is a linear transformation. Let me just write it here. Linear transformation. So if you fix the first slot, if you fix the second slot, plug in a particular vector W, then when you substitute V in the first slot, it becomes a linear mapping from V to R. Needless to say, combining 3 and 2, we see that there is nothing special about fixing the second slot. You might as well fix the first slot. You will still get a linear transformation. An inner product space is nothing but a vector space along with an inner product, like so. Now, I mentioned that the norm for Rn, which is the most interesting vector space from our perspective, comes from the inner product, the standard dot product on Rn. But more generally, whenever you have an inner product, you automatically have a norm that arises from that inner product. Before that, I just want to give a basic exercise. Show that when you take inner product of V and 0, you always get 0. Okay. Now, the inequality that allows us to show that you can get a norm out of the inner product is called the Cauchy-Schwarz inequality, and it's a rather important inequality that crops up almost in all parts of analysis. It's one of those tools that you must be familiar with in and out, and you must know how to apply it and when to apply it at all times. Okay, let V be a vector space over R equipped with a norm, not a norm, sorry, equipped with an inner product then norm V, which is by definition equal to, you take the inner product of V with itself and take the square root, is a norm on V. Okay, of course here by square root I mean the positive square root. Throughout I always will take only the positive square root. Now to actually prove the inequality, so this just says something stronger than the inequality. So to be precise, more precisely, inner product VW, if you take the absolute value, remember the inner product will give you a real number, is less than or equal to norm V, norm W. This is the actual Cauchy-Schwarz inequality, and from this Cauchy-Schwarz inequality you will be able to get that it's a norm. Let's prove both of these facts together in one single stroke. So this is the actual Cauchy-Schwarz inequality, okay, which immediately gives the fact that this definition of norm indeed gives a norm. So this will indeed be a norm from the Cauchy-Schwarz inequality. So let's first prove the Cauchy-Schwarz inequality and see how the triangle inequality follows from the Cauchy-Schwarz inequality. The other properties of a norm are rather obvious, and I'm going to leave it to you. So before we begin the proof, let me make a remark that since this inequality is of paramount importance in all of analysis, there are manifold proofs of this. And it has, I mean, through my career, I have seen at least a half a dozen proofs. There are probably dozens, and all of the proofs will require you to memorize something or the other. Some of the proofs claim to be more conceptual than the other, but still you have to remember something. So I'm going to present the proof that requires the least memory. Okay, so proof if V or W is 0, then we are done. By the previous exercise, it's rather trivial to see that inner product V with W will be 0, which will obviously be less than or equal to norm V, norm W in this scenario. Okay, now assume neither V nor W are 0. The only part you have to now memorize is consider W to be x by norm x, not x by norm x, there's no x here, V by norm V minus W by norm W. Okay, just consider this vector and take the inner product of W with itself. So all you have to remember for the proof that I am giving is the fact that you have to consider this vector. Actually, I shouldn't call it W because I've already have W on the right hand side. So let me just call the next or the previous letter U. Okay, so all you have to remember this, you have to define this auxiliary vector U, which is just V by norm V minus W by norm W, and take the inner product of U with itself. Okay, we already know that by the condition that this inner product is positive semi-definite, that inner product of U with itself is greater than or equal to 0, and by the various properties of the inner product, you immediately get that this is equal to V inner product with itself by norm V squared minus W inner product with itself by norm W squared minus 2 inner product V with W by norm V, norm W, and immediately you see that this quantity, this quantity V inner product with itself is just norm V squared, and similarly this is just norm W squared. Okay, so you just get so I made a slight mistake. This is just plus, there's no negative sign here. So you will get 2 minus 2 inner product V with W by norm V norm W. Okay, I think I put too many parallel lines. So to make sure that I do not make the same mistake again, I'm going to put a dot in between. And this immediately gives, so this immediately gives the Cauchy-Schwarz inequality. Schwarz inequality. Now let's move on to the proof that the Cauchy-Schwarz inequality actually proves that the definition that we gave, that norm V defined to be a square root of V inner product with itself, is in fact a norm. So all we have to do is to show that triangle inequality is satisfied. The fact that norm V is always greater than or equal to 0 and is equal to 0 if and only if V is 0 is rather obvious. Let me just prove the second property also for completeness sake. So the second property says that we have to show norm CV is mod C mod norm V. In our case, the definition of norm CV is nothing but CV square root. Now we already saw that if you fix the second slot, this is a linear transformation in the first slot. So this is just C power half V comma CV power half. By symmetry, I have already remarked that if you fix the first slot, it's going to be a linear transformation in the second slot. So this will just give you C VV. And note that we are actually taking the positive square root every time. So what will actually happen is that, so to be 100% precise, I should in fact write it like this. And I should write this second quantity as C power C squared inner product V with V the whole power half, which is nothing but mod C norm V. There is no comma here. That's it. So the proof that whenever you take a vector and scale it, the distance to the origin scales in the way you expect is rather easy to prove. Now finally, for the triangle inequality, this is going to be an immediate application of the Cauchy-Schwarz. What you do is you consider norm V plus W the whole squared, which is nothing but inner product V plus W with itself, inner product V plus W. Immediately expanding using the fact that this is linear and all that, you will get V comma V plus 2V comma W plus W comma W inner product. And again, this is less than or equal to norm V squared plus norm W squared plus 2 norm V norm W, where I have applied the triangle inequality, not the triangle inequality, where I have applied the Cauchy-Schwarz inequality. And this is just norm V plus norm W the whole square, which is what we wanted to show. Okay, so this shows this norm is indeed a norm. Now let me end this video by remarking that inner products are very special. It is not always true that whenever you have a norm, that norm comes from an inner product. That's not always true. The importance of inner product spaces that I'm sure you're familiar with from linear algebra is the fact that on inner product spaces, not only can you measure lengths of vectors, but you can also measure the angle between two vectors. So these are spaces on which you have some type of geometry because you have both angles as well as distances. The most general type of space in which you have both angles as well as distances is what is known as a Riemannian manifold. And on this Riemannian manifold, all the usual notions from classical geometry like area and volume make sense. So Riemannian manifolds are some special spaces in which you have inner products on each tangent space. So I will not say more because this is well beyond the scope of this course. This is a course on real analysis, and you've just watched the module on normed vector spaces.